Okay, what I have decided to do now is to solve some tutorial type of problems. That means I want to train you to think about the concepts that I have been teaching you in this course through examples, detailed worked out examples. So, it is possible that some of you would have found the course, I mean the actual lectures a bit fast in terms of the pace of presentation. So, maybe many intermediate steps were missing and they were implied, and you probably had a difficult times in places to fill in those missing steps. So, it is important nevertheless, even if you are confident of all those steps, it is important for you to test your understanding of the concepts by working out some of the examples that I am going to be presenting right now. So, these examples go to the heart of the subject, and they kind of make sure that you understand the concepts at the end of the day. So, you can confidently claim you understand statistical mechanics. Okay, imagine you have 2n label sites on a line. So, the idea is that I am thinking of a straight line here, and there is a lattice, and for convenience sake I am going to assume that the even number of sites. So, the number of sites are 2n dot 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 2n. So, on each site there is a spin which can be up or down. So, for example, I can have a situation like this. So, I can have a situation like this, some can be pointing up, some can be pointing down. So, the idea is that that if a spin points up, its energy is epsilon, if it points down, its energy is minus epsilon. So, for example, if in this configuration the energy is one is up, the other is down. So, you just count how many ups are there and you subtract it with the number of downs. So, you see there is one more down than up. So, the total energy is minus epsilon here. Okay. So, in general it is going to be this. So, the total energy is going to be the number of ups minus the number of downs. So, the total energy is 0. So, the question is find the entropy of the system if the total energy is 0, and also find the canonical partition function at temperature T and the average energy at that temperature. Okay. So, now let us think about the entropy of the system. So, if the total energy is 0, what is the entropy of the system? So, we have to calculate the number of ways in which the total energy of the system can be 0. So, the number of ways in which the total energy can be 0 if there are as many sites which have upspin as there are number of sites that have downspin. So, the question is how many ways can you accomplish that? So, the answer is clearly you just have to look at the combination of, because the sites are all labeled. Remember that the sites have specific labels. So, you can tell each site apart from the others. So, as a result you just have to count the number of combinations of selecting n sites from the total number of sites, which is 2n. So, you can choose to assign those sites with up spins. So, then you are forced to make the others down spin. So, you select n of them to be up spin and the others to down spin. So, the question is how many ways can you select n sites out of 2n sites. So, the answer is the combination of 2n taken n at a time. Okay. So, the binomial coefficient. So, it is 2n factorial over n factorial squared. So, now this is the number of ways in which you can select those sites. So, now the entropy is defined as the log of this number, and so that is the entropy. So, that answers the question. So, I hope this is clear to you, because this is one of the fundamental concepts in this subject, the entropy concept. So, if you are having difficulty calculating entropy for such simple systems, then you should revisit some of these issues and learn them properly until you are able to answer these questions on your own. Okay, so the next question is find the canonical partition function at a temperature T and the average energy. Okay, so so if the system is allowed to exchange energy with the surroundings, then its energy is not going to be fixed. So its energy is not going to be fixed, and so all you can do is find the average energy of the system. So the question is, how do you do that? So the way to find the canonical partition function is to take the trace of e raised to minus beta times the energy in terms of the microstates. So remember, the microstates are the configurations of all the sigmas. So now you trace out over all the microstates, and we do it in the usual way. You know that you can write this as the product of e raised to minus beta sigma I, and then you have to trace over all of them. So that means you have to sum over all the configurations. And I have showed you earlier in the lectures that it's possible to interchange the product and the sum, and you can interchange it in this fashion, and then you take the sum over sigma I plus minus 1 e raised to minus beta sigma I. So this sum is precisely twice cosine hyperbolic beta, and the product, if you take the product over 2n sites, so it's like multiplying twice cos beta with itself 2n times. So that's basically raising 2 cos hyperbolic beta to the power 2n. So now the average energy is given by the standard relation in canonical formalism as the derivative of log z with respect to beta with a minus sign, and so as a result you get this result. Okay, so you can examine various limiting cases and convince yourself that this makes sense. Suppose beta is very small, that means the temperature is very large. So if temperature is very large, you expect a kind of randomization of the spin. So you expect roughly equal number to point up as they point down. So when beta is small, you can see the average energy tends to 0. But then conversely, if beta is very large, so temperature is very small, so you can expect the system to be in the ground state. That means you expect all the spins to point down. So that means you expect the energy to be minus 1, minus 1, minus 1 for all the spins. So as a result, the total energy you expect it to be minus 2n. So if beta tends to infinity, which is temperature tends to 0, so this becomes 1. Tan hyperbolic infinity is 1, and so as a result the average energy is minus 2n at very low temperatures and it's 0 at very high temperatures. So it's correct. So we are able to reconcile it with our intuition, and so it makes sense. Okay, so that is the first problem regarding the concept of entropy, and to some extent the canonical formalism also appears in this example. All right, so now the next example is slightly more challenging, and it relates to finding again the entropy of the system, but now the problem is as follows. Imagine that there is a cube here, where the corners of the cube, at the corners of the cube, so remember there are 8 corners. So at each corner of the cube there is a charge that is placed, and so the question is, I want to find the so I am not going to tell you how many charges there are. So you can have a system with variable number of charges. So you can start with 1 charge, 2 charges, and a maximum of 8 charges. So you can have all 8 corners occupied, and of course we are going to assume that the corners are all labeled. So that means I know which corner is which. I know this is corner number 1, corner number 2, corner number 3, corner number 4, and that way. I mean, I can kind of label them in some way. So So, the corners are all labeled, but the charges are identical. So, I am going to ask myself, so if I have say 2 charges, so the energy of the system is by definition the electrostatic potential energy of the system. So, the charges repel each other and they have an electrostatic repulsion, and that is going to be the energy of the system. So, I am going to ask myself as a function of the energy of the system and the number of charges. So, if I tell you the energy and tell you the number of charges, I want to know how many ways there are of distributing these charges at these corners in such a way that the energy is that particular value. So, that's going to be the number of microstates, and the log of that is going to be the entropy of the system. So, the question is, how do I calculate this? So, take for example, let us start with a simple example. So, imagine that there are 2 charges. Okay. So, there are 2 charges. So, if there are 2 charges, you can either choose to place them here and here, for example. So, that means you can choose to place them at sites 2 and 3, or equivalently 2 and this, or 1 and this. So, it could be any of these. So, along one of the edges. So, that means the 2 charges are on the edges. So, that way you can get an energy which is this one. Okay. So, that is called U 0. So, and A is the side of the cube. So, you can get an energy of that form, E squared by R. But then, so that is one of the possible energies. So, the other possible energy is if you decide to place them here and there, for example. So, you can place them here and there, and you can get E squared by, see, this distance is what, square root of 2 times A. So, you can have a situation where the energy is this, but you can also have a situation where the energy is right at the diagonal. So, you can have a charge here and one diametrically opposite. So, there so you can also have an energy which is U naught by square root of 3. So, that is also possible. In fact, these are the only things possible for 2 charges. Okay. So, these are the only energies that are possible. So, the number of microstates, for example, with the energy which is this. So, if this is the energy, then if there are 2 charges, the number of microstates is 12. So, you can imagine that there are 12 ways in which you select this, then you can, so there are 12 ways you can select pairs of corners. So, you can just figure that out yourself. Okay. So, it is easy to convince yourself that 12 ways of doing it, and the entropy is just log of that. So, it's the entropy is log 12 if the energy is U naught by square root of 2 and n equals 2 is the number of charges. So, if in general we may construct a table if there are many more charges, and well, not many more, there can only be 8 at most, but then if there are more charges than 2, then things become complicated, because there are many more possibilities for the energy, and so we will have to construct a table, and so the table is as follows, and this is the table, and so you see the table says of course, see, I have purposely omitted one charge. I mean, if there is one charge, there is no fun, because the potential energy, you need a minimum of 2 charges. But I have also interestingly omitted 7 and 8. See, 0 charge I have omitted, 1 charge I have omitted. So, if there is only 1 charge in the system, it is uninteresting, 0 is even more uninteresting. But then the question is, why have I omitted 7 charges and 8 charges from the table? See, that is because there is something called particle hole symmetry. That means that so you can think of 7 charges as one positive charge. So, you can think of a missing charge as a hole, just like you do in semiconductors. So, if you populate that corners with all 8 charges and you remove one of them, so you get actually 7 negative charges, but that is equivalent for all practical purposes with one positive charge. So, as a result, that because so combinatorially it is identical to studying one negative charge one positive charge has the same combinatorics as one negative charge. So, 7 is uninteresting because it corresponds to 1. I mean, it's analogous to 1 because 7 is just absence of one. It's absence of one charge from a cube where all the corners are occupied by charges. So that's equivalent to one charge. So as a result, I have omitted both 7 and 8, and 0 and 1 are obvious why I have omitted them. So now, as a result, I am going to start populating this table, starting from the number of charges with number of charges equals 2, number of charges equals 3, and number of charges equals 4, and then rapidly after 4 my work is significantly simplified, because when its number of charges is 5, remember that 5 is same as the combinatorics of 5 charges is same as 8 minus 5, which is 3. So, I do not have to populate this row at all. I just copy paste the row containing 3 charges and fill it with the 5 charges, and I take the row that I have populated for the number of charges equals 2, and I copy paste it on the row containing 6 charges, because 8 minus 6 is 2. So all I have to do now is populate these 3 rows, okay, this up to 4. So long as I do this, then I am done. So the question is, how do I do that? So now I have to list all the possible energies that are seen when there are 2 charges. So like I told you that if there are 2 charges, there are only 3 possible energies. One is u0, which is e squared by a, and the other is u0 by square root of 2 when they are diagonally opposite, and u0 by square root of 3 when there are they are as far apart as they can possibly be. So now you ask yourself how many ways there are in which you can achieve an energy of u0. That's going to be 12. In fact, I wrote a small program which does this in a language called Mathematica, and it's something that you should do yourself. So I'm not going to constrain you to any specific language, so you can write your own code and come up with these results. So it's just a question of combinatorics. So you have to, it's better to write a computer program to churn out these numbers rather than doing it by hand, because firstly it's tedious, and secondly, and because it's tedious, there's a chance you'll make mistakes. However, if you write a program and you test your validity of your program using simple examples, if it comes out right, then it's unlikely that it's going to be wrong for more complicated situations. So that's typically how people do it. So they test it out for some obvious limiting cases and then cross their fingers and hope for the best. That's typically, it's never going to go wrong most of the time if you're a moderately experienced programmer. Okay, so this is 12 is the number of ways in which you can rearrange the microstates to get energy u0 by square root of 2, and it's 12 is also the number of ways you can achieve an energy of u0, and there are only 4 ways in which you can achieve an energy of u0 by square root of 3, and all the other columns are empty because there's no way you can get any of these other energies that I have mentioned there. Okay, so what about the other energies? So I'm talking about what about the other number of particles? So there are 3 particles. So if there are 3 particles, then the possible energies start off with this one, which is I hope you can see this. This is nothing but u equals 2 plus 1 over square root of 2 times u0. So where does this come from? You can easily guess where this comes from. This is u0 plus u0 plus u0 over square root of 2. So that implies that there's a charge at one location, there's charge distance a apart So which means that there's a potential energy of U0, and then there's another that's diagonally apart. So you see that there's a pairwise interaction. Okay, so if you have a situation like this, so this pair has potential energy U0, this pair has potential energy U0, and this pair has potential energy U0 by square root of 2. So put together, that's the total potential energy. Okay, that is this example. Okay, so like that you start populating. So if that's the energy, then there are 24 ways of achieving that. So it's going to be very painful to list all of them. That's the reason why you should write a program to list them. So similarly, you start getting all these other possible energies. There's the U0 by square root of 2 plus U0 by square root of 2 plus U0 by square root of 2. So that's 3 times U0 by square root of 2. So there are 8 ways of doing that. And similarly, you will get one more where there's a diagonal thing. There's 1 by square root of 3. That's at the other end of the cube diagonally. So there also you get 24 ways of doing it, and all the other energies are impossible for 3 number of charges. So now again, if you have 4 charges, then again the number of all different energies are possible, and now there are many more. If there are 4 charges, you have so many more energies that are possible, and they're all listed here. And it's 4 plus square root of 2 times U0 and U0 times 2 plus 3 by square root of 2 plus 1 by square root of 3, and there is this possibility which says that it's 3 plus 3 over square root of 2 times U0, then 3 plus square root of 2 over 1 plus. So there are all kinds of possible energies, so you should look this up. So you have 1, 2, 3, 4, 5, 6 possible energies when the number of particles is 4, and the number of ways in which you can achieve say this energy, which is 4 plus square root of 2, is 6, and you can achieve the energy which is 2 plus square root of 3 by 2 plus 1 by square root of 3. That energy is achievable in 24 ways. So like that you populate this table by preferably by writing a program. That's how I did it, and I used this software called Mathematica, which is very useful for doing this type of calculations. And then I told you for 5 and 6 I didn't do anything. I just copy pasted the 3 row into row 5, and of course here you have to take this with a grain of salt. This is not really the energy, it's actually the maximum energy minus U. So the maximum energy is when all the 8 corners are occupied. So if you have 5 charges, the energy is not the same as 3 charges. So if you have 5 charges, it's the same as the 8 charges minus 3 charges. You see, that's what I'm saying. So the maximum possible energy, minus this. Okay. So however, the omegas are the same. Okay, the number of ways in which you can populate those locations are identical to 5 is identical to 3 as far as omega is concerned. So 6 is identical to 2. So that's how you do it, and so this is a moderately challenging example which I feel that you should learn to do properly, so that you will understand how to. So the log of omega is entropy. So you will be able to understand the combinatorial basis for entropy. Okay. So the other topic that I kind of I have used frequently, but maybe not explained its derivation all that well. I explained somewhere once, but it wasn't fully convincing. So I'm going to explain it again properly. and this is called Euler-Maclaurin formula. So, the Euler-Maclaurin formula is frequently used in physics, although many times authors and teachers don't call it that, because in the maths community it is known as Euler-Maclaurin formula, but we kind of use it without calling it anything specific. But it's important to know that that there is a systematic way of deriving. It's not some hand waving approximation, but there is there's a proper way of understanding how this comes about. And so it so happens that there's a series which tells you, so Euler-Maclaurin formula is basically a method which enables you to replace a discrete sum by an integration. So, typically because discrete sums are harder to do than integrations, so which seems odd, but then think about, look, if it's a finite sum, then it's by definition simple, but I am talking about an infinite sum. So, infinite sums are actually limits of finite sums. So, and those limits can be hard to calculate. So, as a result, however, if it's an integration, many times there are lots of tricks you can use to analytically evaluate integrals, but there are fewer tricks you can use to evaluate infinite sums. Alright, so it's nice to know that you can convert an infinite sum to a integral, and the way you do that is through the Euler-Maclaurin formula. So, the question is, how do you do this? So, the way you do that, firstly I am going to state the Euler-Maclaurin formula. So, Euler-Maclaurin formula states that the summation of Fi over from I equal to 0 to infinity is the same as integrating from replacing I by x and integrating x from 0 to infinity. Well, we have kind of most of the time stopped here, we have equated this to this, but in fact that's not strictly true, that there are additional terms. And if you can convince yourself that typically this is always there, but if you can convince yourself that these can be neglected, then this has a lot of use, because you can directly use this. Okay. So, but then if you cannot convince yourself that these are small, then you will have to evaluate them. But then keep in mind that these functions and their derivatives are to be evaluated at exactly one point. So, it's not going to be that difficult, and keep in mind that these coefficients are rapidly diminishing, and there is a good chance that you won't be going terribly wrong if you truncate this series after a certain point. Alright, so so the question is, how do you derive this series? So, this is exact. So, I mean, if you continue forever, it's exact. So, the question is, how do you prove this? So, my method, of course, is I mean, there are many ways of doing this. In some of the maths books, you will find that this is a special case of what's called the Darboux's formula, which is just obtained by integration by parts. So, I mean, those may be probably more mathematically rigorous, but I am going to use a method which is simpler, but probably not very rigorous. But I feel that a physics audience will appreciate this derivation a lot more than they would some more rigorous derivations. But then you should also learn those other derivations which are favored by mathematics people. So, my derivation is as follows. So, I am going to write f of x in terms of its Fourier transform. So, and then this makes sense only if I know how to calculate g given an f. So, it so happens that you can invert the Fourier transform in this fashion. So, this is called the Fourier transform and inverse Fourier transform pair. So, this is well known in physics and frequently used. So, I am going to try and see if I can rewrite. So, okay, I skipped a slide. Okay, so look, I am going to replace x by I. So, you will have to excuse me, or maybe I will replace it by m. So, f of m is going to be e raised to I k m g k d k. Then I am going to sum over all the m's from 0 to infinity. So now notice that the summation of m of e raised to I k m is nothing but, okay, from 0 to infinity is 1 over 1 minus e raised to I k. So I can kind of rewrite this in this fashion. Okay, I'm going to first sum up to n. Okay, so I'm going to sum up to n and then integrate later. So I have replaced x by m and I have summed up to n. Okay, so I got this answer. So because it's e raised to I thing, so I can replace rewrite in terms of its real and imaginary parts. But now this is important because I can't really sum up to infinity, because remember that the geometric series converges only if the mod of, say if it's r raised to m and sum over m from 0 to infinity, it converges only if mod r is less than 1. But here in this example, r is e raised to I k, where mod r is exactly 1. So I can't really sum up to infinity. So what I should do is sum up to a certain value called n, and then finally take some kind of a limit as n tends to infinity. So now this limit, strictly speaking, doesn't exist in the mathematical sense, but we use our physics intuition and say that, you see, when n tends to infinity, we kind of intuitively argue that cosine squared kind of becomes half, because if cosine squared k n by 2, see, cosine itself oscillates rapidly. So it oscillates rapidly between negative and positive values equally. So when n becomes infinity, cosine k n by 2 averages out to 0. Okay, so because it's positive as frequently as it's negative, and when n tends to infinity, it kind of rapidly flips between being 1 and minus 1. So on an average, it's always 0. But then if it's cosine squared, it's between 0 and 1 most of the time. It's always between 0 and 1, and it flips between 0 and 1 so rapidly that its value is the average between 0 and 1, which is 1/2. So same with so in case of sine times cos, it is nothing but 1/2 of sine of k n itself. And I told you that because sine of k n oscillates rapidly between -1 and 1, it averages out to 0. So now with those ideas, so I'm going to use the trigonometric identity here and write this as sine times cos. So I'm going to pull this sine n k by 2 out, because there's a cos there and so on. So I've done all that, and using this idea and using trigonometric identities, so I'm going to write sine of 1/2 of n plus 1 k as a sine of n k by 2 cos k by 2 plus cos n k by 2 sine k by 2. Okay. So I'm going to write all this. So I'm going to write sine cos plus cos sine. Okay. So if I do that and I use all these identities, I end up getting this equation. Okay. So that's one idea which I am going to keep under my thumb. So now also note that if I take this formula and put x equal to 0, I get an integration which is this. So if I take f of x and put x equal to 0, I get this. Then if I integrate f of x, take this, integrate f of x from 0 to infinity, because it's so integral of dx e raised to I k x from 0 to infinity is basically 1 over I k with a minus sign, because at infinity it oscillates and becomes 0. So that's our physicist way of doing things. So so you get this result. So minus 1 by I k times the rest of it. So same with, if I differentiate with respect to x and put equal to 0, that's easier. I get this. I differentiate thrice, I get this. So I'm going to keep this also under my thumb. And now I'm going to do this. I have to apologize, the slides got flipped. This should have come later. Okay, so now notice that there's a cotangent, well, yeah, there's a cotangent here. So this plus this adds up and becomes this, because this is nothing but cotangent. Okay, so it becomes this. So now notice that this is nothing but f0 by 2. So now I have to manipulate this. So I'm going to expand cotangent k by 2 in powers of k. So when I do that, I get this series. Okay. So I'm going to insert that series here, and then when I do that, you see, lo and behold, I start getting the terms that I was staring at earlier. Namely, I get this. Then the case, when I do it this way, so this becomes, this result. There's a k downstairs. There's a k downstairs here also. So it becomes this, and I get these other terms. So you see, so the sum over all the i's from I equal to 0 to infinity becomes this Euler Maclaurin series. So it becomes this integration. So it becomes this Euler Maclaurin series. Okay. So it becomes this. So it's this plus this plus this plus this and so on. So I hope you are convinced by this derivation. So this is an important formula that's used again and again in physics, and it's worthwhile to know how it was derived. Okay. The other thing that I have used extensively in this course, which I again probably didn't explain too very well, and but then I'm going to try now. This is called the saddle point method. So the saddle point method, of course, again is a bit of a special case, which it doesn't do justice to the word saddle point. In this case, it's merely a maximum. It's not even an extremum, it's a maximum, let alone a saddle point. So saddle point comes about if you are trying to do integrations over complex functions of a complex variable. But in this case, I am only going to restrict myself to integrations over a real variable, real functions over a real variable, in which case there's no saddle point, there's just a maximum. So now imagine that I want to calculate this integration over, so there's an integrand which is g of x times e raised to n. So this n is very large. So the idea is that n is huge. Then I want to calculate this integration, I want to perform this integration from between x1 and x2 when n is large. So the idea is to write a series for I of n in powers of 1 by n, where it's assumed that f of x has a maximum. So the idea is that, let's imagine that there is an f of x which has a maximum between x1 and x2. Okay, so it goes through a maximum. So I want to calculate this integration when it goes through a maximum and n is very large. So that's when the saddle point is very useful. So it's clear that the maximum contribution to this integration comes from regions where the integrand is very large. So the integrand is, because n itself is huge, so the integrand is dominated by the regions where fx goes through a maximum near the peak. So since I have choose to denote the location where the function f of x peaks as x0, so I'm going to therefore conclude that its first derivative is 0 because it's a maximum, second derivative is a negative because again it's a maximum, not a minimum. So then I can Taylor series expand f of x around x0, and I end up getting this result. Alright, so I get this result, which is basically this Taylor series. So the first derivative is absent because it's a maximum, and notice that because g of x is assumed to be regular in this interval, and the dominant contribution clearly comes from this integrand here. So I have chosen to replace this by x0 and pull it outside. So now I am going to do a change of variables. I am going to set y to be this quantity because the exponent involves x minus x0. So I am going to set that equal to y. So then I can replace just through change of variables, I can do the integration over y instead of x. So I am going to integrate over y and from y1 to y2. Okay. So where y1 is this and y2 is this. Notice that x1 is less than, so x1 is here, x0 is here, okay, and x2 is there. So that means x0 is between x1 and x2. So because of that, you see y1 tends to minus infinity because n is huge. Remember that n is huge. So if n is huge and this is negative, so y1 tends to minus infinity, and also because n is huge and this is greater than 0, x2 is greater than x0, so this is more than 0, so this is positive, so y2 tends to plus infinity. So as a result, I am at liberty to approximate this by minus infinity and plus infinity, and this becomes approximately so notice that this is negative. So this makes perfect sense, and then I am going to be able to write this in this fashion. So this is the saddle point. So you see that for the most part I have, so if I take log of in, this is going to be n times f of x0 plus a whole bunch of other things, which you can sort of ignore, because well, the only reason why you shouldn't ignore it is for dimensional reasons, because this may have some dimensions which is but this is dimensionless. So otherwise for the most part you can ignore this. So notice that n is very large, so this is roughly ignorable. Unless you have dimensional issues, then only you should take this into account. Alright, so this is basically the the baby version or the real version of saddle point as opposed to the complex version. So the real the actual saddle point occurs in a situation where you are integrating on the complex plane over functions of a complex variable, but here it's not a saddle point, it's a maximum, but it's the ideas are similar. So the whole idea is to kind of replace the exponent of the integrand by its maximum value or near the maximum value, so that you can perform the integration as a Gaussian, and then you just live with that. Okay, so that was the tutorial for today. So hopefully you will join me for some of the other tutorials that I am going to discuss. So I am going to start explaining to you various other concepts through examples, so that way you will be able to better grasp the lectures that you have been listening to. Thank you. Hope to see you next time.